Hi everybody, today we're going to have a look at Hamiltonian and semi-Hamiltonian graphs. They're a little different from the Eulerian graphs we did in the last video in that they are concerned with primarily with vertices instead of with edges. So let's start with Hamilton. Hamilton is who it's named after, and it was named after him because he investigated problems that involved visiting each vertex once in a dodecahedron using closed-edge paths. His game was iconic and ended with this branch of graph theory being named after him. So let's have a look at some graph theory. So is the following graph Hamiltonian, semi-Hamiltonian, or neither? Now we've got A, B, C, D, E, F vertices and 1, 2, 3, 4, 5, 6 edges. Now primarily Hamiltonian problems fall into two groups. We have Hamiltonian graphs or semi-Hamiltonian graphs. In the same way we have Eulerian graphs and semi-Eulerian graphs. So with a Hamiltonian graph, it's important to travel to each vertex and end on the same vertex where you start. It's a closed path. And with a semi-Hamiltonian graph, it's important to travel to each vertex, but not important to end on the same vertex. In either case, each vertex and edge can only be traveled once, and that's why we call them paths rather than trails. So, let's have a look. Is the following graph, the one we looked at before, Hamiltonian, semi-Hamiltonian, or neither? So let's look at the graph theory. A path on the graph is a list of vertices connected by the series of edges where edges and vertices may not be travelled more than once. So A to B, let's get this into a cursor. A to B, B to D, D to E, E to F would be a path. A closed path would start and finish on the same vertex. So if we started at B, we would go to D to E to C to B, that's a closed path. We didn't repeat any edges, we didn't repeat any vertices. An open path, like A to B, B to D, D to E, E to F, does not need to finish on the same vertex. Now what's a Hamiltonian path? Well, a Hamiltonian path traverses all the vertices once in a graph. So it would go to A, B, C, D, E, and F without traveling the same edge or vertex more than once. A Hamiltonian cycle is a closed Hamiltonian path. So that just means it starts and ends on the same vertex, but goes to every vertex and every edge, goes to every vertex, no, that's still not right. A Hamiltonian cycle goes to every vertex, but doesn't travel any edge more than once. It doesn't have to go to every edge, but it can't go over an edge more than once. Similarly, a semi-Hamiltonian path is the same as a Hamiltonian cycle, except it doesn't have to end on the same point. So it will still visit every vertex, and it will only travel the edges at most once. A semi-Hamiltonian graph then is defined as a graph that has a semi-Hamiltonian path, but not a Hamiltonian cycle. If it had a Hamiltonian cycle, we'd call it a Hamiltonian graph. But if it doesn't have a Hamiltonian cycle, but does have a semi-Hamiltonian path, then we'll call it a semi-Hamiltonian graph. Okay, end of the theory. Let's try it on our example. Is the following graph Hamiltonian, semi-Hamiltonian, or neither? Well, we can go A to B, B to D, D to E, E to F, and now we get stuck because we can't go back because that would be traveling E to F more than once, and we'd be reaching the vertex E more than once as well. So there's no path on here that allows us to get back to A, or if we started at B, to get back to B and traverse every position. So given the Hamiltonian cycles cannot repeat edges, if we ever reach A or F, it's impossible to return without repeating an edge. Thus, it's not a Hamiltonian graph. And I've missed out a full stop there, so let's stick that in. Now, given a Hamiltonian path cannot repeat edges or vertices, even if we started on A and finished at F, it would be impossible to reach one of C or D. So for instance, if we went A, B, B, D, D, E, E, F, we would have missed C, and there's no way to get back. And if we went A, B, B, C, E, C, E, E, F, again, this time we would have missed D, and there's no way to go back. And if we don't end on A and F, we'll have to repeat either A, B, or E, F. Thus, it's not a semi-Hamiltonian path either. So this graph is neither. But what if we wanted to make it into a Hamiltonian graph? Well, we'd need some way to get back to the start, and we'd need some way to get to the either C or D without repeating. So if this time if we went A, B, B, C, C, D, D, E, E, F, and then F, A, this path here, we would have a Hamiltonian cycle, then this would be a Hamiltonian graph. And we should note that we don't have to travel BD and CE for it to be a Hamiltonian graph. It just has to have a Hamiltonian cycle somewhere within it. Similarly, if we wanted a semi-Hamiltonian graph, we'd have to make sure that there wasn't a Hamiltonian cycle in this, and there isn't because there's no path from F to A. And we'd have to make sure that we can get from A to F via all of our vertices without having to double back. So A to B, B to C, C to D, D to E, E to F, we have a Hamiltonian path. And given we have no Hamiltonian cycle, it's a semi-Hamiltonian graph. And again, in this case, we haven't traversed BD and CE. I hope that helps you understand the difference between a Hamiltonian graph and an Eulerian graph in conjunction with the previous video. And I will see you in a future video. Thank you, everyone.